and then put on the share. All right. So we're going to talk about the oscilloscope today. And so again, you can watch, you can do, or you could try building things, and we'll get some more kits and things involved. So today we're going to talk about a little bit about the safety, uses of oscilloscopes, the names, the types, what you want to measure, typical layouts, and then we'll just go through an example using one or two oscilloscopes so you can see what they look like. So basically an oscilloscope looks at how a signal changes from over time. So it does time domain measurements. And it's used to observe a voltage changing with time, and then it can also be used to measure frequency and also to see if there's some DC component of an AC signal, and you can do that by setting it up in various different ways. So one of the things you need to know is what you need to know what you're going to measure. So if you have a radio that's running on 13.8 volts, can things can something go wrong? So one of the things you have to remember, like if you're looking at the RF output of the radio and putting it into a 50 ohm dummy load, then 1 watt will produce about 21 volts peak to peak. And then if you go up to 10 watts, you get 67 volts, and 100 watts is like 212 volts. And then, if you're getting up into the 1500 volts, 1500 watts, you're producing about 750 volts peak to peak. So, voltage is a concern, and oscilloscopes are usually rated around 200 or 300 volts, maybe some up to maybe 600 volts. So you're going to have to look at what's your rating of the oscilloscope and the rating of the probes, and you might have to get a special probe if you're starting to look at some of these higher voltages. One of the things again to remember is that most of these oscilloscopes are plugged in to the AC outlet, and that means that the case and one end of the probe is grounded. And again, some of the less expensive, the price range of an oscilloscope, can go all the way from like $30 up to about $100,000 or more. And the biggest thing is the frequency range and also the voltage range. So some of the the ones you can get like for $50 might only have a limit of about 10 volts, while others might have a limit of closer to 500 volts. And then some of the less expensive models don't have any input protection circuits built in. So if it's rated for 10 volts and you put in 15, you're most likely going to damage something, and that's the end of the oscilloscope. Again, here's an overview of ground safety. This is the same video I was referring to last week, where it's titled, "Don't blow up your oscilloscope." So here's some interest on if you're interested in watching that. So the thing to remember is that one wire is connected to ground, and I'll be showing some probes. So all measurements are relative to ground. Now, if you have a battery operated radio and you're not connected to the ground, then it doesn't make that much of a difference. But again, you have to realize that the case is ground, and you could get, if you happen to touch the case, you could, get yourself a shock. So there are things like differential probes available that allow some measurements of high voltages, but these probes will probably cost you about $400 or $500. And there is also a possibility, if you have a 2-channel scope, to use 2 channels and then subtract the 2 signals from each other. But this is going to be a little bit difficult to do. So that's one of the things you have to be careful about if you're doing differential measurements. So types of oscilloscopes. It started off with just having a computer sound card, and you put a signal into your audio sound card, which is limited to about 5 volts, and you could look at your signal there. So that's an easy way of doing it. I would recommend getting an external sound card. So if you do put more voltage in than 5 volts, you blow up the external sound card, not the sound card in your computer or on your laptop, which most likely you can't fix. And then, it all started off with the analog CRT tube, which is basically a miniature TV tube, and you get your signal here. So these scopes are readily available at, lots of them at the swap meet. You can get them. They're somewhat limited in frequency, so you need to look at. Um, but some of them don't provide, any out digital readout of what's going on. They just provide you a picture of what's going on. Now they've gone into digital scopes. So the one we'll be looking at is similar to this one here, which is a Ryko scope. Rigol scope. So there's benchtop ones, there's handheld ones that are becoming available now, and here are some of the less expensive ones that you can get. And now also this is quite popular, where you have a box which you connect to the computer, and the computer does all the displays for you. So these are the different options available these days. Again, it depends what you want to look at and what's the frequency range and the price that you want to spend on it. One of the things is that, some of these handheld scopes can be isolated, but remember that the BNC connector here is one of your signals, and if you happen to touch this, you could get a shock. And also, you should be using a 10 times probe, and we'll look at some of the signals coming from a times 1 and a times 10 probe. So when this is basically how the oscilloscope works. If you consider this like an old TV tube, you have an electron gun here. It sends out electrons that go down here and hit the display here. And this is a phosphorus screen, and the screen glows. And then you have vertical plates and horizontal plates. So when you have a signal coming in, it goes through a probe. It goes either through an amplifier or an attenuator, and goes up to these two plates here. So depending on the polarity, it will cause this dot either to go up and down on the screen. Now you also take that signal and you get it and you put it through some sort of triggering system, and you put it through some sort of sweep generator, which generates a sweep. And then it goes to a horizontal amplifier, and then it goes up to these plates here. And this causes your dot to go across the screen. So going up and down is basically voltage from your signal, and then going across the screen is representing the frequency of your signal, and also the frequency of how it's being displayed. And that's how the analog scope works, and the digital scopes works in the same way, except it uses software to do all of these things. And so some of the important parameters that you want to look at is the bandwidth of your scope. And, 10 years ago, 300 kilohertz or 1 megahertz was sort of the top of the line for, amateurs, non-professional scopes. Like the scope I've got here is listed at 70 megahertz, but in actual fact, it only goes up to 20 megahertz. After 20 megahertz, the signal starts to go down, and 70 megahertz is the 3 dB point. So nowadays, most of the oscilloscopes that you can buy, which are in the $300-400 range, are typically 1 or 200 megahertz now. And even the high end of the low end scopes for amateurs tends to be up, getting up to like 501 gigahertz range now. And then you can get 10 gigahertz and 100 gigahertz scopes, but you're going to pay for those, and those could be 50, $60,000. The other thing you need to look at is the maximum voltage. So typically, most of the scopes are in the 1, 200, 300 volt range. Some of your less expensive ones that, are less than $100 could be in the 10 to 50 volt range. So again, you need to look at what are you trying to measure. And then the other thing you need to look at is your minimum voltage sensitivity. Most oscilloscopes are, 10 millivolts or 50 millivolts. Some of the less expensive ones are like 100 millivolts. And then, more of the expensive ones get down to 1 millivolt. So some of the new features is that since it's all controlled by software, you can set up things using one button, and we'll be showing this. And, and you can also do like frequency measurements, and you can do mathematical functions between signals. And typically you can get a 1 channel, 2 channel, 3 channel, or a 4 channel scope. And then you can also get look at digital signals like from an Adreno.
A
For
question, Roy.
Yes.
Yeah, what you mentioned earlier, the bandwidth, 500 megahertz and all that up. You're talking digital scopes now, not analog scopes.
Yeah, I'm talking mainly digital ones because these are the ones that are readily available now.
Yeah, they're basically the only ones. Yeah, it's very hard to find an analog scope. In fact, it may be impossible to get
Yeah,
one that high frequency.
yeah.
They
I mean,
might,
some.
they might
Yeah,
go to 20 megahertz or something. That's about it. And all the rest are digital. They're sampling scopes, as they call
yeah, yeah. I mean, so you'll find some of the digital scopes at some of the swap meets. I mean, some of the analog scopes at the swap meets now, and some of them may give them away for free, but you might only be able to get up to like 1 megahertz or 10 megahertz. So that's something you need to look at. And also again, what are you going to use your scope for? Like if you're going to, looking at for basic electronics and playing with different circuits, maybe 1 megahertz or 5 megahertz may be enough for you. If you're getting, if you want to build the HF transmitters, going up to 30 megahertz, which means probably going up to about 100 megahertz, 150 megahertz would probably be okay if you want to look at the signal. If you really want to get into UHF and VHF, that's where you need like a gigahertz, 1 gigahertz or more oscilloscope. And I mean, you're going to pay the price for it. And, a lot of people aren't experimenting with VHF or UHF because the test instruments are quite expensive. There are other ways of doing it to see if it works or not. So it depends what your goal is in if in getting an oscilloscope. So you have to put some thought into it. What do you actually want to measure? And then some of these oscilloscopes also have a digital signal where you can have 14 to 20 leads, and you can hook it up to like an Arduino input and output and see the different pulses, and then it can decode signals for you. Saying is this a USB signal, or is this some other protocol communication back and forth. So some of those scopes can do that for you too. Um, Okay, so your typical analog scope for that was available, and you can find at your swap meets will just give you a waveform, and by the height of the waveform, you can set this like at 10 volts per division, and then you have to count how many divisions there are to determine what your volts is. So, if it's 10 volts to division, this is 2 divisions, that would be 20 volts. And you would do the same thing for frequency. You would see what your period would be across each one of these divisions. So you would count where one cycle would be and, calculate it that way. Your newer scopes, will display something like this and then have a whole bunch of parameters listed up the side and up at the top, telling you a whole bunch of different things like, here's 1 volt per division, your voltage is 2.49 volts. You're, looking at, here they're looking at 2 signals. You can add them or subtract them. Here, time is this way, voltage is this way, and it's telling you, your peak voltage, your frequency. So you can get a lot of information out of your oscilloscope these days if you go with a digital model. Some of the Tektronix used to be the gold standard. Now you have other people, Fluke, Rigol, Allergen, Signal, Lint, Unity, Circuit Test, Owen, all making oscilloscopes. But you get what you pay for. So one of the things is the bandwidth, maximum, minimum voltage, with your digital oscilloscopes now, how much memory do you have, and what's your depth of your memory, and then, what sort of features you're looking for. Do you want it to be able to add and subtract channels and do a whole bunch of mathematical formulas for it? And then also, how many channels do you want? You want 1 channel, 2 channels, 3 channel, 4 channel, and I think you can even get 8 channel scopes these days if you want to look at 8 signals at a time. Here's again some YouTube videos. Here is some information about getting wrong measurements using the wrong probe, and something about X1 and X10 oscilloscopes. We'll cover a little bit of this shortly. So next week we'll talk about the Tinkercad. So any questions before we turn on the camera and see if we can actually see the oscilloscope? So let me pull up the camera and see what we get. Okay, all of you should be seeing the oscilloscope. We're still having a little bit of a problem. Let me move it. Let me just move this over here. Move this over here. So I've got to change the lighting around a little bit to get that glare off the screen. But so this is typically. Let's try to focus here. Okay, so this is just a second. Yeah. Okay. So this is typically your oscilloscope. Before we turn it on, let's just look at some probes. So I mean, you have a choice of a number of things you can do. For example, you can have like a BNC connector, which you connect to the scope like this, and then you just have some leads like this, and then you have alligator clips at the end, that you can connect your signal. This is likely, can be used for low frequencies, but it's likely to pick up, a lot of noise and things. You can twist the wires together to reduce the amount of noise that you pick up. I mean, this is one way of doing it. The other way of doing it is to use like a BNC type of cable, and you can have either a BNC at both sides or like an alligator clip on the other side. Now, most likely you're going to run into some impedance problems with this, because the impedance of your line is 50 ohms, and typically the output of here is like 1 mega ohm, unless you get some of the newer, more expensive scopes where you could adjust it from 50 ohms to 1 mega ohm. So that's one of the things that you have to look at. Or what's recommended is you actually use the scope probe that comes with the scope. So you have your end connector here, which is a BNC, and this is shielded, so if you happen to touch it, you don't get a shock. Then the other end of the probe looks like this. So this is your ground. So make sure you always connect this part to your ground of what you're measuring. And then this goes to where you want to measure the signal. So here it has a little clip. You can pull this off, and you get a point that you can point to a circuit and test it that way. When you're going to high frequencies, this length of lead is going to present a problem for you. So it's going to interact. The other thing that you have on here, which is not that easy to see, is an X1 times an X. So X1 means it goes straight into the oscilloscope. X10 means that there's a 9 mega ohm resistor plus a capacitor in there. And that's what's recommended to do. So let me just see what this is connected to. Okay, so this is set to X10. So what you have on your oscilloscope is basically your inputs. So this happens to be four channel inputs. Now, depending on your oscilloscope, you have your vertical control here, which controls your vertical signal. You have your horizontal control here, which moves the signal across this way. Vertical is this way. And then you have your triggering function here. And we'll look at some of those things. Now, some of the oscilloscopes might have a knob for each one of the channels. This one has one knob for each one of the channels. So to change the thing around, you're going to have to push different buttons to get that. So let's see what happens when we turn it on. And let's see if we can see something. I might turn off the light for this. So it's going through. Let's see. Well, this okay. Uh, okay, so that's what you're going to get as your oscilloscope. So it's showing that this channel one is on. So I could turn channel one off, for example, and you don't get anything on the screen. Now, so one of the things is when you first turn on the oscilloscope, you may not see anything. So a lot of the oscilloscopes have a button up here. This one happens to be lit, called auto. Oh, sorry, no, auto is this one over here. This is the run stop function that can tell you whether you're running or not. So, if you don't see anything, you know, and, even your analog scopes have like a beam finder. So you can press the auto, and it'll look for something. So what it's doing now, it's set at the most sensitive level of, because there's nothing set in. So so that's what you get. So I mean, it is possible. Like the intensity could be turned down so that you might not see anything because your intensity is turned down. Or, for example, this controls the precision of where the signal is. So, I mean, it could be that someone's adjusted it so it's off the screen and you're not going to see it. So you have to bring that down. And then the other thing is on your horizontal side, someone could set it up so that the horizontal is actually off the screen too. And so you'll have to find where it is. So pressing the auto button is the best thing. Now on the side of the scope here, you have like a 1 kilohertz test signal, and that's used to calibrate your probes. So what you can do is you can plug this into your channel. And as you can see, it's picking up a whole bunch of noise around here. Um, so what you can do, I mean, you can, go here and turn down the the scale setting. But what you can do is you can hook it up to your signal. And so what you do is you push the auto button again. And so it's now using a sine wave, a square wave, to calibrate your probe. Now your probe has a capacitor built into it, which you can adjust. So so what you do is you get yourself a screwdriver here, and you stick it into the end of the probe where there's a hole. Just a second. Let me just take this off so I can just see what I'm doing here. Okay, so some of them have the capacitor here, and some of them have the capacitor here at the probe. So what you do is you take yourself a screwdriver, and like if you're adjusted like this where it goes up off the screen, um, or it goes down the other way, your probe isn't calibrated. So what you're trying to do is to get a square wave like that. And that means the capacitance is set. So you should use the same probe all the time for that particular setting. Otherwise, it's going to change. And so what it's telling me here now is so one of the things you have to uh, look at is in is this value right here called probe, and it's set now to times 10 because your probe switch is now set to times 10. And if it's not set right to what your probe is, you can get the wrong value. And then it's telling me here it's set to 500 millivolts scale, and it's telling me that the frequency right here is 1 kilohertz. Voltage peak to peak is 3.08 volts. Voltage RMS is 2.09 volts. And then over here you have all of these different parameters you can you can set up. If you want to measure rise time, fall time, how wide the signal is, you can all do that. And over here, the other thing you have here is your coupling. Let me see if I can get that in better focus. Okay, so you have a choice of DC coupling, which basically looks at the AC signal and the DC signal. And when you switch this over, you can set it to ground. So you know where your ground level is. So you can set your thing up here, for example, so that your ground is at the center of the scale. And now when you switch this over to DC, you'll see that it's above the ground, so that means there is a DC component to the signal. If you don't want to look at the DC signal, just set it to AC and leave it at AC. And you'll probably maybe want to adjust it a little bit again just to see. It's fairly good. Um, so um, so then this controls the position. Oops. This knob here controls the position of where that waveform is on the screen. So
Hey,
ideally,
Roy,
yes,
is there a focus control on the oscilloscope?
No, it's clear. It's just that the camera for some reason is not
Oh,
picking.
their oscilloscope should have a focus control for its own screen.
Yeah, it's fine.
Oh, okay. Just thought I would check that. Some of the
No,
flare
yeah,
signals,
no,
or you
it
can turn down the brightness a bit or something.
no, it's no, the camera for is not picking it up. Um, it is fine here, so I'll have to experiment and see if I can get it a little bit clearer next time. Yeah, I don't know why it's not focusing um, on the.
Well, that's pretty good. That's probably as good as you're going to get. Yeah.
Yeah, it doesn't seem to want to focus on the display for some reason. I don't know why. I'll have to see if I can figure it out. No, this is the best we're gonna get for now. I'll for the next one video, I'll see if I can get that somehow better.
Hey, Roy,
Uh,
try turning on your main light. It might help with the exposure.
okay, let me see if I. Uh,
No, it didn't help. Sorry.
no, it's I'm gonna have to. Maybe I need. Maybe I'll have to go to some side lighting or something. No, I mean it seems to somehow. Um, yeah, it's for some reason it doesn't seem to. Let me just try this. No, that seems to actually be worse. Yeah, I don't know why. Um, I'll have to see next time to see uh, it focused better. So this controls the position of your thing. Um, so typically, you want it in the center. This controls your amplitude. So, when the signal gets too small, you don't have enough signal to actually do your triggering. That's why you're not getting a waveform. So as you increase, you know, the signal gets bigger and bigger, and you may want to look at like the top of a waveform or the bottom of the waveform. So you could, do that by just moving this around as how big you want to see it. And then over here is your frequency control. So when you look at it, this is what you see. So you can see there's a whole bunch of cycles. So then you have to look at what you want to actually look at in terms of the waveform. Like here is typically one cycle. But if you wanted to look at the edge in more detail, or if there's some noise on the edge, you could look at it that way. So you've got that control. And then again, you got positioning here where you can move the things up and down. And most of your controls are like your triggering is going to be automatic. Like this is the triggering. So when you look at the triggering, it's fine. But you may want to like trigger at the bottom edge or something like that. Like here we've lost the triggering now, so you can't see it. But if you're looking for some noise or something, you can use like an external trigger and trigger it on the noise and see if you can see your signal. So it has quite a lot of adjustments, and you can also force the trigger and change it to like different levels, and these things change here if you want to trigger on a positive edge or a negative edge. um, so and the other thing, and then also over here, you can store your signal, but also over here you have your measure button. So if I push this button here, oh, just a second. Okay, so I have the measure button, so I have to go here and turn it on. Oops. This is okay. So, I'll turn the measure on. So, you up here you've got, although you can't see it too clearly, but you've got a whole bunch of measurements for channel one. You've got maximum voltage, minimum voltage, read peak to peak, T op, base, amplitude, average, VMRS, area P. So there's 34 different parameters you can measure on your on your uh, on your oscilloscope. Um, and then you've also got statistics. You can measure on and off. What's your high value, your low value. Um, and then the other thing I wanted to show you is you have also a mathematical function here. So you can add, subtract signals, and do a whole add the two signals together. And so we'll turn on the Fourier transformation, which is like a frequency analyzer. And so what you're seeing now here is so this is your time. At the top here is your time display. Bottom one is now your frequency display. And you're getting a whole bunch of harmonics coming off of the square wave. And you can set it up so you can measure what your harmonic level is. Um, So, there's some useful features. So this is telling me, this is the main harmonic, um, main signal frequency, and then there's some other signals involved with the Fourier transformation. And so, and then you can also have, if I can turn that off, then you have a whole bunch of different mathematical functions. You can add signals together, you can subtract them, you can, do some logic signals, you can, take the integral or the differential of the signal, you can take the square root of the signals, log of the signals. So, it allows you a lot of features that you can look at. Basically, it's, to look at what the signal looks like, what the voltage is, and what the frequency is. And then you've got, you can stop it here. You can do like one shot, which just does a one shot of your of the waveform, so it'll hold it. So if I take this away, it's recorded. Um, so you have all these features here, and so that's one oscilloscope. And now we have this one here. Just a second, I got. So this is another one that you can get, which is um, one you can get. Now the thing here with this one here, you have to be careful, is that the probe here has no insulation on it. So if you happen to connect something on to the black lead and you accidentally touch this, you're going to you could get a shock. So let's take a look at this one. So I actually haven't used this one too much yet. Kelly has one of these also, and so we'll just hook it up to the same signal base. Again, you have the same probes. These probes are a little bit better in that you can see X1 and X10. So we'll just hook that up to the ground. And take this up here. And then this one here has an auto button too. And for some reason, let's see. Okay, we've got too many wires here, so let's get rid of one of these probes. Stick this into channel 1. Okay, here we're now we'll press the auto button, and there's your signal. Now this one actually has the adjustment on the probe here, so you would adjust it. Oops. Again you would adjust it here for your signal. This one seems to be pretty good. So there's your other oscilloscope. This one is about $110, and again it gives you RMS 2.02. This one says the same value, and then frequency 1 kilohertz. So you can get a big scope like the Rigol, or you can get something like this, and it'll give you. I disconnected one of the grounds here. So you can get, and this one actually has a higher frequency range than the Rigol. This one has 2 inputs. This one has 4 inputs. This one does a lot more mathematical for variations, and also you can plug in your logic analyzer down here where you can look at signals. But this is a good scope for measurements and gives you all the values that you want. So any questions on that? So that was a brief introduction into how an oscilloscope works. So let me just stop the recording.